So, till now we have learned about the aromatic compounds. We have gone through the introduction and we saw that the aromatic compounds are the ones which have high degree of unsaturation, and one of the common aromatic compounds is benzene. We have seen the structure of it as well. We have talked about the resonances, resonating structures of benzene, and then commercial preparation, how coal is converted to coal gas, coal tar, and coal tar is converted to light oil. Light oil is then further converted to benzene. Then the laboratory preparations are one of the important points that we have learned, that is using sodium benzoate, and I'll be showing you the mechanism in the further course. And we have also seen how do we prepare using the sodium sulfonic benzene sulfonic acid as well, and then even you're using phenol and diazonium salts and ethylene NXN as well. So we also saw that benzene is having 4 degrees of unsaturation, so you can just count it. Degrees of unsaturation is nothing but the number of double bonds and the total number of the rings in a compound in a structure. In the structural representation. So double bonds, there are 3 double bonds and there's one ring, one outer closed ring. So it amounts to 4. Characteristic reactions are the electrophilic aromatic substitutions. We have also seen about that. We have seen the mechanism of it as well. How does it happen, and it's a 2-step process. Why the reaction is slow, I have talked about that as well. It's due to the bond order, which is greater than 1 due to the resonance. And we have seen about the reaction. We have seen the reaction coordinate as well. It is potential energy versus reaction diagram. And we have also seen about the rate. That is the electron releasing group and electron withdrawing groups. To give you a rough idea, I'll give you the electron releasing tendency and this thing as well, just to in the further lectures. I think you'll find it after some time. We'll be going through that, which is moderately deactivating, activating, which releases better electrons, which group attached. Okay, now coming to the monosubstitution. So first that we are going to learn monosubstitution. Okay, let me write monosubstitution. So monosubstitution we are going through, and then benzene. We have benzene. So let's say taking X2, that is halogen. It might be Cl2 or Pr2, and we see that we get this type of product due to the EAS X plus HX. I've spoken about this as well over here. Can it HNU? So in this, what is the electrophile and what is the nucleophile in X? X2 can be any of these two. X plus is E plus, and Nu minus is X minus. Okay. It is not this thing used along with X2 is FeCl3. This supports the EAS. How does it even happen is, I'll show you that thing. The Cl2, let's say if we have Cl2 and FeCl3, FeCl3 being a Lewis acid, it accepts Cl minus, and you get FeCl4 minus, and then Cl4 Cl plus, or Cl4 plus Cl plus. Okay. So the reaction conditions are low temperature. I'll tell you why we consider low temperature, and absence of light, This is because to avoid free radical mechanism as well. And then rate of this is K into benzene, concentration of benzene into concentration of Cl2, as we have spoken already here. Yeah, in this part, instead of E plus we have X plus, that's all, or Cl2 plus, whatever. Now, as we are considering the halogens, we see the reactivity. Let's see the reactivity order for halogens for this reaction. Fluorine is very reactive compared to chlorine, bromine, and the least reactive is iodine. So as I have given the order as fluorine being more reactive, this direct fluorination turns out to be explosive. And iodination being very less reactive turns out to be a reversible reaction, and you see that as it is a reversible reaction, we more get what happens is, okay, I'll talk about it as well. Let me talk about the iodination. I2, this is going to be reversible as it is very less reactive, so it's all due to the energy aspects. We get this, and this Hi in presence of an oxidizing agent OA, this turns out to be I2. We take along with this, let's say the OA, what are the OAs? I mean the oxidizing agents. HNO3, Hi3, HGO, and then H2O2. These are some of the oxidizing agents. Why do we use an oxidizing agent? Is because just to increase the yield of iodobenzene. Increase the yield of this iodobenzene, we use oxidizing agent as it follows the forward reaction. But iodine, and also you are supposed to note that iodination shows isotopic effects. No other halogenation shows isotopic effect. We see that C6H6 is more reactive than C6D6. C6D6. For fluorination, bromination, and chlorination, we see that C6H6 is almost same reactive as the C6D6. It's almost same C6D6 as well. Why this is happening? Because iodination is going to be reversible. And one of the important reaction to note over here is, let's say we have something like this, that is benzene, and we have ICl, that's an interhalogen compound, halogen compounds, and we use AlCl3 or ZnCl2. Yeah, I forgot to mention that FeCl3 is a Lewis acid, so instead of FeCl3 you can use any other Lewis acids as well over here. Okay, that's Lewis acid. Okay, so we are using AlCl3 over here, or you can also use ZnCl2. We get this. How do we get this? Thinking logically, AlCl3 being a Lewis acid, strong Lewis acid, it is in it is in search of electrons. So electron density on chlorine is more due to its electronegativity. So this AlCl3 goes and carries, takes off the Cl minus, and then AlCl4 minus is caused, and then I plus is left around, which acts as an electrophile. Okay. Even similarly, BrCl, taking the same Lewis acid, let's say AlCl3, we get, please guess the product before I write. It would be bromine, because of the electronegativity. Now we found that the fluorination is going to be explosive. So what would be a better method to prepare fluorobenzene? So I'd give it under a note section, which terms we would take benzene diazonium salts. Okay. So there are two types of reactions that you can learn as well. One is using BF3, HF, and some heat. Another one is by Ki for it. This is for iodination. This is for fluorination. Okay. You get this, and due to iodination, you have this. Okay. So we spoke about the halogenation and halogenation process. Halogenation of the aromatic compounds. Now let me talk about nitration as well. Also told you that the important point over here is that the electrophile is going to be the X plus, and sometimes you might be given questions in which you are supposed to find the electrophile in these type of reactions. In these type of reactions, you might be in need to find the electrophile. So the electrophile of this would be Br, not Br plus, not Cl plus, not Cl plus. Okay, just remember that. I have given the logic as well. It's because of the electronegativity order, which is like this. Fluorine is more electronegative. Chlorine, bromine, iodine. Okay, now coming to the nitration. For nitration of aromatic compounds, we use nitration mixture which is concentrated H2SO4 plus concentrated HNO3 taken in 1:1 ratio. Okay, so let us see the reaction. I think the mechanism followed by all these reactions is similar to the first mechanism that I have shown in the electrophilic aromatic substitution section. It all follows the same. Only thing is, instead of E plus, you need to take the respective electrophiles. Guess the product, NO2 and H2. Okay. How you might find it a bit difficult. You might be assuming that NO3 minus, it would break as NO3 minus and H plus. I mean, you might make a rough guess, but let me talk what is happening when it is combined with the H2SO4 as well. We have something like this, H. Okay, this is the nitric acid, and we have H2SO4 as well. Am I right? So what happens is the H plus from H2SO4, the H plus from here goes and attacks this lone pair, and we get HO plus H NO2 plus HSO4 minus. And if you observe superficially as well, you might be able to find that this is forming up one of the stable product, a very most stable product, that is H2O from here. So from here you get H2O plus HSO4 minus, plus we have NO2 plus. Due to the kinetics, this NO2 plus do not combine with HSO4 minus, if it's a question. So this would try to act as an electrophile, and go attack the benzene. Okay. So we found that electrophile is equal to NO2 plus, and there's no isotopic effect. Is absent. Why is it absent? Because you have observed that the reaction is not reversible. It is not staying in equilibrium at every stage. So can assume that. I don't need to assume. So this shows that the isotopic effects are absent. So the rate of reaction is same for all types of isotopes of hydrogen. The other reagents that can be used apart from H2SO4 and HNO3 are some of the reagents. NO2, ClO4, CH3, CONO2, N2O5, HBF4. These are some of the reagents that can be used apart from H2SO4 and HNO3.